morning.
He was in his office and the door was closed.
So I haven't seen it. So is there something difficult you've heard from that?
I want to give him a few more minutes.
Yeah.
We could try to call him, but
It wouldn't do any good if he was not in his office.
that's true.
Okay. And it's very hard to arrange things like this with all these busy people, so I'm amazed. I'll just take a few minutes to just introduce, why we're here today, and then turn it over to François to talk a little bit about the background project for the Geometer's Workbench, which is what we're going to look at. And then I'll come back and play a little bit with the Geometer's Workbench, and at the end, hopefully to wrap up with some questions of people here, but especially the geometers, the mathematicians here, thinking of the mathematicians as a kind of a design group, design focus group, about what ideas the mathematicians can come up with on how to do a next version of the Geometer's Workbench that would be aiming at something that we can actually use. Okay, so so a few years ago, I want to thank Terry Winograd especially for making it possible for me to come and just hang around the different projects that Terry and Pat Hanrahan have been involved with. And one of which is this mural project, this interactive mural project, but another one is this thing being built downstairs, which is a room which maybe people can describe later on. I also want to thank very much Rafe's support over all this time. We'll see if all this faith will, how it will pay off, but it's been very
It
good.
better, huh?
So you each go walk home with one of these, right? And I also have to thank very, very much François, because this really builds on a huge amount of work with François and also the other people in the group. And basically, the Geometer's Workbench is a very minor corollary of a huge amount of work done by these people. So it's almost, like an afterthought. But I'm amazed at what can be done as an afterthought. Let's see. So at this point, what do you say? Should we just turn it over to you and start this thing?
Sure.
Okay. Without too much preamble.
It's not really an afterthought for me. My research project is to try to understand how people interact with these large high-resolution display surface. And so it started something like 2 years ago, as Shinwei pointed out. And for my thesis, I'm exploring two venues. One is collaborative setting, which is, for example, a brainstorming session where several people are around, exactly like that, around the board, and try to come up with as many ideas as they can. And I do that with IDEO, which you may know it's a small design firm, not small, but one of the biggest design firm, and which is in Palo Alto. And the second venue is a more peer-to-peer communication, and basically the Shinwei project was perfect, where you have two students, or a master and a student, who try to understand the problem, or someone who try to explain the problem to someone else. The interesting thing for me also is that Shinwei require probably high resolution, because you will see the interface we design. We use small multiple, meaning that we will have many pictures to try to understand the structure of a specific space. And so it was basically, for me, it was interesting to have these two aspects. First, high resolution, so a lot of information to display on the surface, and then an interaction, which is peer interaction, where something like 2 persons interact directly to the surface. I think that the best way is probably to show what we did. It would be more. So, just a comment. The interface will look relatively bare, and very little text and stuff like that. We're using a relatively new graphic system, and text is not a strong point. So yesterday night we had a wonderful interface with a lot of text, and it crashed every 5 minutes. So we removed most of the text, and now it kind of runs for a long period of time. So sorry for that.
I think most of you have heard this before, but the motivation, the driving idea behind this is to start with a blackboard, and to start with a basically passive surface where anything you write will work. That this is a small rejectable that we write, so you can take anything. And then opportunistically, some kinds of strokes will be interpreted by the machine. So the question is, what can you do when you have a blackboard that begins to interpret part of what you just wrote, and other parts you can just draw and leave it on the screen, like paper or chalk and blackboard.
explain the interface.
So why don't you explain?
So in the interface we have three, and again, it's where I would like to see more text. But, so we have three panels, and the panel here is used to enter simple strokes. I mean, first I should ask, do you know what this thing is all about, and did you?
I should say that? Okay, fine. So the model for this is very simple. The idea is, this is like, this would be a domain, this is a range, and from here we select a mapping. So, so basically this is like a graphicization of a very simple thing, like down on a piece of paper. Well, f maps from x, space x to space y. All right. So we're just playing with various ways to work with a very simple, basic notion that we have to work with all the time. The difference you can see here is that this is done graphically. There's no typing, there's no keyboard, no mouse. All right. So we try to see how far we can push this idea purely with gestures. Okay. So domain, range, and what we fill this with first objects which will come through the map into the range. Okay.
So in domain I can draw freely, or I can enter simple shapes. In the range, in the mapping, I can explore different possibilities for the mapping. So the mapping is a family of functions with two parameters, which are, say, u and v. And I can explore this parameter space by just clicking. And as I do, you can see that there is a smooth curve.
You know, you can't just come up. I mean, this is not, what do you say? I think it's better to just come up and look at the board.
So here, for example, I'm exploring the space of torus, and you will see that as I go in that direction, the torus is more and more complete, and as I go in that direction, it becomes thinner and thinner.
Excuse me, I can't really hear what you're saying.
Sorry. Oh, yes. So so we have a very two parameter space. Here it's for the torus. So as you see, as I go in that direction, I get a torus which is bigger and bigger. You see it's a very small section here, and it's almost full here.
No, I thought Chinwei said the middle domain was supposed to specify a map.
Yes, what I should say, to be more precise, is what this is a space of maps to choose from. Okay, and the family of maps, there are several families, and each family is parameterized by two parameters. Okay, and the parameters basically just map to various constants. So, for example, in this case, the two parameters that we can use is how much of the torus we show, and basically one of the radii.
So
of
that-
the anchor rate. So those are the two parameters we can vary.
That torus is a parameter space for a family of maps.
Of course, precisely, it's the one parameter family of maps, and the other parameter is basically how much of the torus we map.
But what are the maps?
These are just, the maps are going to be basically, well, we should show it. We should show it.
So when you can pick exactly one of these parameters, I mean one point in this space, and then you will see the map you are using. So as you see now, we have one torus. Go for it.
Okay, so this is the image of this square, this whole domain, and under this map. And
So what about this extra squiggle? I didn't see what you were doing on the domain.
It's a little bit dim, but and if you look at this here, as you move around, you notice that the squiggles have appeared. So let's draw one. Let's clear this up. I'm sorry, I'm not transparent. Let's show you. Okay, let's draw something bigger. Okay, so I drew an L. That object, that L has been mapped under the mapping into the image of the mapping. The image of the mapping is a torus. Okay. So basically every point in this
Do you see
two-dimensional domain.
the stroke on the surface?
No, I don't.
A little bit. See from
Yeah, I know. So I really recommend that you go and see, because there is a stroke on the surface, which is
There it is.
the map of.
There's a company see. Okay. So no, it's important to come here. Okay, so you see I drew this O at the top and then I did the L. So you can look at the O, there it is. That's at the top. And this L is reversed. The one feature is reversed, which is also why it's dark on the outside and bright on the inside. For this torus, how they fix that. That's my thing. Okay. So actually it's interesting to do that. So now we can change. This is basically a bunch of points in the domain. I just mapped them under the chosen map, which in this case is somewhere around here where the red cross is. now I can go through and change the map. So, for example, let's look at this one. Okay, that's the image. That's the entire image of the map. And let's pick a different one. It's pretty different. Let's pick the fact for us. And select something. There we go.
Shinwei, how are you picking these different maps? These are already there?
Yeah.
Or
Yes, I'll say
somehow-
something in just a second. So I choose a particular mapping, and then let me just make it different. More obvious. Okay. The torus is the image of the square under the mapping, and I can put in points inside that and see what happens to a point. The mapping goes to right there. Okay. Now, how do I choose the mapping? Well, actually, we have several families, so let's choose another one simple. Let's go to here.
What is that little diagram that comes up when you?
It's you should come up with it's a little expansion system that François invented that you can look here. So basically, this is how I'm going to choose families of mappings. So let me start again. Take this mouse. Or François chooses this mouse. I don't imagine it's too large. And then when I go to families, this is this. These various families that are already created pop up. So let's go to a very simple class, the spheres. Okay. Now if I go around and explore the space, these are different ellipsoids. And we're going to find out what's happening now. Of course, it's related to these, but it's more fun. So here, the center are basically expanded spheres, various sections of it. As you go down, you get less of it. And as you go in the x direction, you vary the distortion. So you choose a map, then you can choose a map. Up and down, you can choose a map that's parameterized by the points that you want here. Okay, so that gives me this part of this. Now it's clear that, I'm just learning how to use this. Basically, I spent 21 hours deploying the system. This is making data understand. Let's put in some domains. Let's put in some subsets of the plane, see what it has to do. So now we know that this is time. This is time. And then we can try some standard shapes. So like square, triangle. As I move around, François gives me a standard shape like a triangle. What I would like to have, or what I would imagine having, would be like a fancy mesh, or polar mesh, or circles, etc. See what we have.
I see.
Great, so you get it back. Now I can change the map to that. It's getting messy, so it's good. So begin to play with this idea. This is of course very crude, but you just begin to get the idea of what we can begin to do, right? In this. Now, of course, this is a toy until we can actually easily change the mapping, right? And here's the part where we just decided it's not part of the research because other people are doing this work. Where in fact we're talking to people like Jim Marble down at Caltech came up to visit for the conference at 3 of you were at.
Did you intend to show us?
Yeah, he saw it.
Did that convince him? He said it's the.
Yes,
he
I'm
knows it.
hoping that he's gonna. Well, no, he's already convinced. It's just the fundamentals. But the point is there is that there's a lot of very, very good work that actually François should talk about in terms of expression, gesture recognition turned into mathematical expressions, formulas. Okay, so there's already work done by people like Jim Marble and other places where you can actually write like this. And crash the system. And where this kind of thing would be interpreted into some expressions that you can see in Mathematica. By the way, all the stuff that's going on is actually being sent to Mathematica in this computation. So they create these services in fact. Would you review this with some okay, so I can go on talking. So while we start, there's more to explore. So one of the things I said early on as a goal for the project was how do we map between gestures on the board and an algebraic representation of the surface? So the very first cut, well, people already have sliders. So you can have a slider, and you slide the slider and changes the real parameter, but it's incredibly cumbersome and completely useless for what what we want to do. So it's still an open field, right?
Just one question, like, why is that? It seems like having two sliders would be the same, really, especially having this parameter in the middle
In
space.
fact, it would be, except that now we have two widgets there that are, how do you say, they're separated from the objects that we're trying to play with. If we're trying to play with function definitions and surfaces, we don't need any other widgets on the screen. In fact, this is an experiment how to do without widgets, like pull down menus and things like that. And
I have a comment on that too. The interface is designed because we have a very simple surface here, but sometimes we have computation which take 5 seconds or 10 seconds in the Mathematica, and then it's almost impossible to try to find your way with a slider.
Yeah.
On the other hand, when you use small multiple, you can sample. It will take a long time for the system to give you the
Yeah,
answer, but it will be there, and then you can say, oh, that's the one I want, or then I want something else. That's why we want that.
yeah, and this was a good idea that François had about small multiples. Another issue, in fact, another issue in a different direction for this is if the system were really fast enough, what I can imagine, right, is doing is, I should not wave over text, is as you draw over a curve in the domain, you want to see the curve go in real time. Or if you set down initial conditions in the domain, you want to solve some differential equation on the fly. So it's really cumbersome to actually go and fill those constants either with a field or, with different text fields or with sliders. It just doesn't work. And people build such systems like ABS. So, but usually those are for engineering applications and just nobody actually uses.
They're very
geometry.
specific purposes.
Very specific purposes. And that's the other thing, specific purposes. So one of the open questions for me at least is, how would we build a gesture system where the user can assign, basically hook up parameters in the model to the gestures on the screen?
Right.
All right, that's just a big question. So this is one first cut. In fact, that wasn't the first idea. The first idea was, should I put back up?
No, it's fine.
First idea was, as you do two strokes, this is something for future. As you, for example, draw two strokes like this, the system should infer that it's a domain, but it's an R2 domain. If you draw three strokes that look like the orthogonal lines of the three axes, the system should infer this as an R3 space. There's other work along those lines. One of them is, in fact, what is called Sketch by Celeste and Confuse. I must have mentioned that in the prospectus a few years ago, and more recently work following on that, which is pretty good. But for the definition of the function f, if we had a math expression editor, we could just write it up on the board, right? And that would be the mapping that you use. And if you want to change it, you'd actually just like in Mathematica version 3, you can actually go in there and just change the actual mathematical expression, the algebraic expression. But those are basically independent components. We have just different ways of getting in there. And this graphical method is just basically the quickest way to do it purely graphically. So we looked at one family, spheres and tori, and let's start with one. Torus. Okay, let's choose. Now let's look at some other families. Like the surface that's immersed. So here's where it begins to get interesting. If you take an immersed surface, let's take a standard shape. Orange is a circle. Let's do that. Practice. Okay. So begin to see something that we can play with here. Okay, see how the loop flows through the sheets. Alright. So let's look at some other examples in this space.
What are these surfaces, by the way?
These are just trig functions. Okay, nothing special about them. They're just trig functions. The only reason I chose them here is because they're pretty and they help self-intersection. Okay. So some other families you can play with here. Sorry, I don't have any CMC surfaces, but it's on the menu. Let's take saddle. Very simple one. Alright. Instead of a circle, of course, we should put in a triangle. And these are equilateral, right? So we can show students that yes, indeed, something happens in the negatively curved surfaces. Of course, if you can project down onto it, that's what right here. Okay. So you can begin to play with these things. Now let's go into.
Why did the vertices show
Oh
cross
yes, good
lines?
question. It's my fault. I use an exponential smoothing. I basically, because François gives me points, individual points. So I need to turn them into a function in order to have them composed with the mapping from R2 to R3. Okay, because basically what I have is basically a map from interval into R2, that's the curve, and then a map from this curve in the plane into space. Right? So I need to compose the maps, which means I need to convert these points into a function. And I use an exponential smoothing function to mathematically do it. But it smooths out corners. So corners, so François tricked me by putting a few more points at the corners. That fools the smoothing function thinking that they actually do a lot. So it's an artifact. Okay, so let's choose a family. Let's see. Normal surfaces. Okay, now we're looking at normal surfaces. Let's see. Let's just explore the space. Here's one. Here's another. Another. This is all very classical, but you can just have a very different way to look at the Bachelor's representation, right? So as we go up and down, this is what happens. You see more and more of this catamount-like surface, more or less. And as you move horizontally, we're basically going through rotation, the by theta, right? So we're changing theta as we go to the right, to the left. Okay, you can see that most clearly, of course, with the top row. Now let's choose one of these. Choose that one. Instead of this triangle, let's find our orientation. I thought this is actually, we don't even need to put in little arrows. See, okay, this is actually common for everyone. Yeah, last night we were thinking, well, how do we know what's top, what's bottom? And so I wrote a little notebook, a little package, a little cell, which we haven't put in there, just to compute the tangents and then draw the little arrows tangent at a given point on the surface. But we don't even need it because we just draw this in the domain, and that's good enough. In fact, let's see what happens to. I'm not expert.
Well, I didn't quite hear you. I don't see your point.
My point is that, you see, we could go in and write code that would give us a nice little set of tangent vectors.
Yeah, sure.
Right, that. But for quick and dirty work, if you just want to know what's the orientation of the domain,
you just do that, and right, and distinguish right.
So we're beginning just today, and we're just beginning to basically invent instruments. See, this is a first step toward basically on the fly to make it in fancy language. This is on the fly creation of an instrument by the user. Instrument being which way is up, or finding the tangent frame to the surface. Okay. Very simple example, but I think it's going to be fruitful at some point. Let's give you another instrument. Let's do this. Here's the instrument. So, I now have a mesh. I didn't even have to ask François to create a standard mesh for me. So, So let's move it around a little bit. Let's try to orient it. Keep it like that. And let's see what happens as we change the mapping. Let's go to this one. You can see what happens to these coordinate lines as you get closer and closer to the coordinate. Come on, surface. No, that's just a floating tile. That's green tiles. Okay, so you get the idea. I begin to draw these various meshes. I can create my own meshes and just see how they behave as I change the map. So very simple things. Like once when David Hoffman was giving a talk on his course on linear surfaces, he was saying, well, he was wondering, he had a different class of families, and he wanted to be able to see, well, what would happen to the coordinate lines as we vary certain parameter. And it was basically it was a simple thing. You could actually, well, it would take some work. I mean, you would just see that these coordinate lines would just be circles, and on the pendulum line just lift as you go through the parameterization. But it would be easy just to do it here, just by putting points. So I think basically that covers the demonstration of the kinds of services we put in already. And the question is now to change the tenor of the presentation from a presentation to a Q&A. Since I think your time here is very precious, so I wanted to take advantage of this to ask basically for suggestions on what we might be able to do with instruments like this, okay, boards like this. Not these particular interfaces that we've shown you, but now you know a little bit about what technology can do. Okay, because at this point it is a blank slate. It's almost literally a blank slate, particularly with a lot of expertise behind it. So, floor is yours.
Well, it seems to me that, something like this would be much more useful if you have a lot more flexibility of how you feed in, what the mappings are and so on. You have, obviously you have to have a library of things on some level to choose from, but, and I guess that's, maybe the only point is you just have a small library there now, and, but in some sense that still seems fairly clumsy how that works, and that seems, and also on this domain side, even as opposed to having I sort of like this thing where you could sort of just have these various standard shapes, triangles and circles, and you should be able to sort of put in various types of grids and so on, and having that be sort of more I guess this stuff is all still fairly primitive, and so it seems very clumsy to manipulate, but I guess that in time it will become sort of much more fluent in that regard.
A lot of things that do like tracking.
Yeah.
Offsets, when you're putting the pin down, things like that. But it's very hard. But that's for sure. In terms of libraries, in fact, this is a point for people in the computer science, which is a lot of this kind of work typically is, how do you say, you want to maximize the gain for the least amount of work. So, what I'm trying to push with this project, for example, is to argue that we actually need to hook this kind of technology to real engines, like Mathematica, which are very slow, but they're well used and well understood by the community in this case. And there are a lot of libraries that have been written by mathematicians for that engine. Okay? And I want to see how far we can go by hooking up some of those existing pieces of work. I have in mind, for example, Jack Lee's work in Ricci, which is actually not so visual, but it is a huge amount of interesting work with tensor calculations. And of course also numerical methods for solving ODEs and PDEs, which we can now make available to a person who's not.
Right, well that in some sense would be the main thing, is getting sort of numerical stuff in there. Simply, suppose, away from purely geometric things, suppose you're trying to study turbulence, water waves, stuff like that, shallow water waves, and you want to sort of really be able to compute quickly, compute solutions of Navier-Stokes, for example,
Yes.
just with respect to different geometries. And that seems to me that would be sort of a fairly useful experimental tool.
Yeah.
for those
So
guys.
what people talk about is to try to factor out that kind of computation to somebody else, that's one piece of machinery,
Yeah.
and have that also merged back onto the screen. So that's interesting work to be done.
Yeah.
And this kind of computational steering is something that people are thinking about in terms of like fluid dynamics.
Mhm.
And I want to basically piggyback off that kind of computational steering idea and say, well, now suppose we put in our own differential equations and to define our flows, then they're geometrically interesting, but use the same machinery to do that. Definitely, that's
But I mean, these shapes that, I mean, they really are coming from a library. You're not sort of computing them at each step. And like when you're sort of,
these one of these.
these ones are, but
Yeah.
when you're rotating it around, you're actually having to recompute it, or is it a set library of things?
So Mathematica computes the shape,
Yeah.
and then you go into the graphic system, and then you rotate the shape itself.
So
Mathematica
that's,
only computes it once, and
Yeah.
after that, the motions are done by graphic system.
So it computes a three-dimensional shape.
Yeah, and then after that,
and then there are the various
projects
projections,
and
and that's something that has to be recomputed as you turn it, right?
yeah, I mean the projection on the display is done by the graphic system.
Yeah.
So Mathematica is not involved. I would say, I mean,
So that's quicker.
That's
Yeah.
much quicker.
That's why you
Because-
that's why you can drag it and stuff.
yeah, this shape again are very simple, but Xinhui has a different set of shape which takes something like 2 or 3 seconds to recompute each
So
time.
each click
And
would
then
be
you cannot interact
Yeah.
directly, so you have to send that to
So the real bottleneck in that is just the slowness of Mathematica, for example.
Yes. It's cuts two ways. One is then see, in fact, even for the minimal surfaces, these were in a sense cached because basically I just did the integration in Mathematica symbolically and then just gave François the
Mhm.
the result. But what I would like to have is basically you actually put your own, choose your own Gauss map, choose your own differential, and have it integrate, which means Mathematica will be even slower. And I actually do the symbolic integration, then put it into form that can be sent over the wire, da 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 da. But it's merely a matter of speed, right? But because it gains a huge amount of flexibility. See, that's the other thing. For computer graphics, it's interesting because basically computer graphics projects will start with, give me the formulas for the surface, equation for the surface, and I'll just plot it for you. But I said, well, that's the last step. What's interesting often would be, well, I want to see, I would have implicit ways of defining the function, or have it done by integration instead, for example. So I need a symbolic engine like Mathematica to compute that first, and then give it to the graphic system. So now we basically have it all the way down the line, from graphics all the way down to the algebra.
One interesting use that I at least see, and obviously since François is here, is also this collaborative use. What do you, how do you envision that?
Yes, well, we talked about this too, and we almost wrote a paper about this, right? So the thing is, this is another reason for using a Blackboard, but this project has that feature in common with other projects, like François' other main project, which is, we could say, well, why not just do it with a tablet and keep, on your own computer? And this becomes really useful when you have 2 people, obviously, 2 or 3 people up here working together. In fact, it's tiring for one person to use this all the time. It's very natural to have 2 people. One person rests and watches, the other person talks and doodles, right? And this allows that kind of really quick, on-the-fly talk. I mean, that's one of my goals is basically support real casual work, not formal work where you submit a tech document to another person over email. This is kind of fine-grained, on-the-fly.
Well, ideally, you'd like to see something like the 2 people are in different locations,
Also this,
for example.
also this. But the point is that the people are in sync.
Yeah.
They're going to work together at the same time with the same common object. So this kind of common object is a way for us to make sure that we're talking about something that we both understand. Well, that's what you do with the board and a piece of paper.
Actually, if I understand you correctly, then the menu in the middle can be just extended by having the user predefine their functions, and then you can feed it in
Yes.
and compute it in advance, right?
Yes. Well, this François' department, this thing about the menu, it can be anything. It can even be characters like summation sign, integral sign, Greek letters, etc. It's not clear how best to use that kind of thing. This is actually an appropriate use because we have a few small number, like 5, 3, 5, 4, things to choose from, and maybe 2 layers. That's enough. Top level, second level. But for anything like real math expressions, it's just I think it just gets complicated. So we need another way to do that.
So we are working on, we are exploring what can we do to enter an arbitrary formula, or maybe not an arbitrary formula, but simple subset of formulas, which basically will give the flexibility you were talking about, where you won't be limited to the library of function, but you will be able to enter a formula of your own, or maybe a
So just having sort of a blackboard, you can just drag over things, drag over
exactly.
symbols, and just put them in place. Yeah.
Another issue. Okay, scoping. Thanks. But there's a thing about scoping which I wanted to play with. Which
What do you mean by scoping?
But scoping means this. If we had a function f equals, can I touch this board? Okay, f equals some formula here. There's another way of thinking about this. Instead of choosing functions from function space, function space, suppose we just wrote down f equals in the formula. All right. We want to change that mapping. Well, what we do is basically write on the side f equals something else, and then now that we have a blackboard system which is live, we can pull that down and pull this into place. So whatever is up top scopes everything down below it, which means that it takes force. So what I can do is take this one and put it to one side, right? So these two objects don't see it anymore, and they see this new function definition. So I can begin to play with the board, really play with the board. And this is something we can do with an electronic board that we can't do with a blackboard. So I'm also interested in how to begin to play with properties of what is alive. Okay. Another thing which is people always mention is memory. That boards like this support storage and retrieval, and that's actually a new direction. I don't know yet how to go about that. One thing is erasure. Like on a regular blackboard, when you erase, it's gone. But maybe with an electronic blackboard, when you erase, it records. Whatever you erase disappears from the screen and is recorded.
Or you can have just a special button when you erase to make it record or to
make it record or to it's like a scanner, And then the nice thing about that is it can also store when you recorded it and who did it, so you can call it back and erase it. But these are just small things. Another thing is elastic space. Elastic space. So some other people like Ken Perlin, a very computer scientist, has worked with different kinds of elastic zoom, infinitely zoom space. But the scoping thing, I think, is the first thing that we can actually play with that really could have an interesting payoff. And there was one other issue. All right, in terms of design, this is a bit of a rant. Often these systems that people use, like Mathematica or list-based things like Maxima, are these very, very deep engines. All right, they're designed with a very specific set of well, not Mathematica. That's not fair. A special purpose program, like some sketching program or something like that, or a spreadsheet program. Spreadsheet program is a good example. They were designed with a very specific set of activities in mind, so they go very far down the road to automating it. Okay, and what I've been arguing with people, or suggesting to people outside the mathematical community, is that the computations that mathematicians do are not something that we want to automate, actually. So this is not a project to automate any computation. It's actually to make a whole field of computations available to a mathematician. So what that means in terms of design is that we're showing you this kind of screen, and we're not showing you a deep, long, automated process to do something, like whatever, compute homologies for you automatically. Well, we can ask other experts, to do that for us with a special package. But to open up basically a field of different technologies, your questions, my idea for the future is that when mathematicians look at this kind of system, we'll be showing them, basically, showing the mathematicians examples where the examples are taken from familiar mathematics, classical mathematics, but transposed to this strange domain. And hopefully, the mathematicians will come up with new mathematical questions that could not actually be explored with traditional technologies, like pencil and paper. That's strategic. So it goes back and forth. At the same time, we come up with new questions, and then we go turn around to the computer scientists and say, well, we actually need to modify the technology a little bit to handle those new questions, or ratchets. That's it. Thank you.
Okay, thank you very much. That's great. Another demo. This one I'm giving. a
The
little
name
harder.
tag, huh?
Yeah.
I'm glad that you guys could come because it's not easy to get everything together.
So, Shinwei, this last point you were trying to make, I mean, I understand what you mean about these very deep applications versus, you know, I mean, what you might call sort of a broad spectrum of things that you can convert easily from one to another. But in some sense, that sort of thing has been around in computing for a long time, and that's just what a desktop and any stupid PC is.
Right.
Right? It's just a way, if you have a lot of applications, it's moving back and forth between them fairly rapidly. And I think that, you know, that
Yes.
need is
Yes.
omnipresent for anybody using a computer.
Yes.
Right? So it's, and, you know, so it's really just the interplay between the deep, you know, the depth of each application and how flexible it is, how integrated it is with other deep applications.
Well, here's the question: is because on the that's a good example because on the desktop, like on a Mac or a Windows machine, what can you do with the desktop other than put a folder icon on it or move it around on it? See.
But you know,
a
it
real
allows you to
desk-
have various things open and, you know, move back
Yeah,
and
yeah.
forth easily. And, you know, that's sort of the point.
And I can see. So the idea was that it is about we lost a lot of stuff that we can do with real desktops when we moved to the Macintosh desktop because we can't scribble on the desktop randomly. We cannot draw on the desktop, and we can't overlay transparencies on the desktop anymore. In other words, the qualities of the desktop, the space between the folders, is basically dead. It's not. You can't do any computation on our behalf. And the nice thing about something like this kind of system is that the white space, the counter space, can actually also be active.
How so? Maybe an example.
So, well, it's supposed to be raised to right rectangles.
Yeah.
Okay, so it doesn't look like a like a window anymore. This space actually is what we think of as a live space. So in here, each one of these cells is actually a window into Mathematica. So if you do this, it actually moves like this. So there's a fair amount of work that went into that. So what it's doing is actually it's talking to, well, it came from Mathematica, but it's talking to the graphics system. But you can imagine as you move and do this kind of stuff, it's driving computations. But in this space, however, unlike the desktop, it's still alive. It actually registers, and you can do work with it.
Well, but
And
those are all because those are sort of hidden
we programmed
things.
it in. We programmed it in.
Yeah.
Yeah. But it's just this idea that the space is like the counter space, white space itself can be computationally supported. It's,
I mean, it just seems a way of sort of more finely using that space. I mean,
yes.
you know,
Yes.
ideally, you know, with the
fact.
desktops as they now stand, you just sort of have a
Right.
number of discrete blocks, and now
Exactly.
this is sort of way of, you know,
Right.
making each
In
pixel do
between.
something
In
different.
between.
Yeah.
Right. In
I mean, it's
between.
always discrete, but just sort of
Yes,
making
yes.
the scale of it much finer,
Yeah,
multi-scale.
I think that, you know, like metaphorically, I'm thinking like walking across this floor, you know, and now the floor is cushiony, so I can do stuff with it. You can do dance steps with actually register on the floor. But some of them are really deep, really big holes in the floor. As so I fall into Mathematica or I fall into MATLAB, you know, I think we can do a lot
God
more.
forbid, right?
Yes, I know. That's really, you know, take a lot of time. Okay.
What strikes me about it is about this is in the desktop, which is a great thing, but basically it's a fancy way of letting you choose from a rather small list of.
Yeah,
it's
that's
like
exactly
It's
it.
like filling out a multiple choice form or something.
Yeah.
At each stage you can click on something, you get 5 choices or 6 choices or something like that. Here you're exploring ways to
Make that
enter
much finer
continuous
grained.
parameter-
Yeah.
I mean continuous things like the curves, the vary things continuously, which on a standard, you know, something like Windows desktop you can't.
It's impossible.
Yeah, you're just inputting discrete data, not any.
No, I think that's sort of the
This is
great.
on tape.
That's sort of the great
Yeah,
promise of this.
It's recording.
This is important. This is a very important thing because this
That's
is
what I was trying to get at, but you said it much better than me.
continuity.
Well, at the beginning, I mean, as of this project, you used to talk about the blackboard, right?
Yeah.
And this feels like a combination of what the blackboard has with certain things that computers can give
Yeah.
you. So the blackboard has exactly these kind of things that you can work in any modality. I mean, you can write, you can have equations, you can draw on it. It is collaborative in the sense that somebody else can go and layer over this, you know. And you know what the blackboard does not have is exactly that zooming in that you suddenly. I mean, it's the human attention that can do that.
Exactly.
Basically, suddenly focusing on a small part and saying, here's really something interesting happening. With this thing, then you can actually blow that space up
Exactly.
and make you fill the whole thing and work down as deep as you need to go and then come back up. And so I still think that the intuition that the blackboard has capabilities that the computer lost or never has had, and these capabilities are valuable and they should be brought back.
Yes, both of these. So this continuous gesture is one very crucial, I think, interesting aspect of this work. And the other one is this idea of superposition, which we haven't played with. But you see, this system can support superposing objects. And so in principle, it's a lot of work. But you see, this is exploded for simplicity. But you can also imagine one of my just driving stories is, suppose when you look at this kind of surface, what do some people talk about in terms of geometric analysis? Well, just like it was with the mall. So I had this compact domain. I define a definition of the surface supported only compactly in that domain, right? So, but as like this is talk. This is just talk. When you write it down in terms of B sub R. Okay. But what you really, what I think about is this. I mean, I'm taking the Rocha section, I go to the surface, I put a blowtorch to it, and I heat it up, and the heating basically is done by a vector field. Okay, let's say it's normal. It has a certain normal, but it has a certain speed, resistivity, curvature, blah, 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 blah. Okay, all this stuff. But this is what some people argue, I really think. I'm claiming this is how people, I think this is how people argue this way. When you write it down in notation form, you see the coding and decoding going on. Okay. So if we want to support casual but rigorous mathematical thinking, I'd like to support that competition as well.
Well, I think actually they argue in both ways. I think they also argue in the notational form.
Yes, it's very,
sure,
and
absolutely.
you can do abstractions from that, which is very powerful. So I want to be able to go back and forth. Exactly.
Yeah.
Both, without switching to a desktop and switching to the paper. Most people will never make the process. It's too costly.
It seems like maybe one thing that you could do would be to try to find a problem for which this was appropriate to solve it, and then figure out what extensions you needed to make in order to solve that.
Yes. Yes. And then that's why I focused on two particular areas. Talking with Rafe. One is CMC surfaces, and the other is minimal surfaces. And the reason for minimal surfaces is just because there's a lot of technology already used for that, notably, Bracke's work and the GMP and things like that. And when I talked to Hoffman, he said, well, frankly, a lot of that work is closed. It's a closed chapter, right? In terms of developing new technology for that kind of thing. But the advantage of that is we know what works and we know what people found to be very useful. And I also know a little bit, in my beginning talk, I took a look at Bracke's surface evolver, and I said, one of the problems was it's hard for us to define our own integrals to blah, 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 blah. This is an open setup. I mean, I would say that in principle, so that's sort of known problems with known techniques and known technologies, and I would want to see how to support those objects, and then put in a few hooks to make it easier to change the integrals that we'd be interested in studying for easily. The CMC surface is more problematic because the technique for generating CMC surfaces, I talked about this with Karsten, depends on, the differences obviously is that the minimal surfaces have a very nice representation.
What is a CMC surface?
Custom curvature surfaces. The custom curvature surfaces, at least the ones I know how to compute, or Karsten and Potier and Oluknop know how to compute, are based on basically a discrete geometry. So they use a discrete version of the conjugate surface idea. And you take a minimal surface, you define this conjugate surface, and then you define all these in terms not in terms of smooth quantities, but in terms of discrete quantities. So it's tricky because I don't want to go to that level. I don't want to quite go to. I mean, I could. I mean, I'm just debating right now how far.
No, I mean ultimately one would, but
But the question is, and ultimately one has to. In fact,
Yeah.
the question is one Xinwei and François is one an automatic software piece of it does the translation for me. That's another piece of work, and this is a good motivation for research. So.
Anyway, how does this, just physically, how does the screen know where you touch it?
We use this device, it's called an e-beam, and you can buy it. It's ultrasonic transceiver on the fan, and the two pods they do a triangulation of the fan.
So
So it's really the screen is not detecting. It's this thing is detecting where
the screen
it
is
doesn't
completely
screen.
passive.
Yeah.
It is, yeah.
Yeah, and so just
So what's behind it? It's like the Wizard of Oz.
Go take a look. there's a little guy in the back.
Okay.
That's right.
In the back.
A little short guy.
Hello, you can come out.
Like the famous chess player.
Yeah. Try and fix those. Well, almost it is.
so it works for sound.
It doesn't transmit sound.
It does. I mean,
It's-
it's ultrasonic, and then you have
Oh, I see.
basically
Okay.
surface wave
Yeah.
on the material, and this guy picks the surface wave.
Oh, okay. Oh, okay. I see.
But you should say more because this whole system is much more flexible than just a particular.
Yeah, I mean that's I designed the screen, but the graphic system has been designed by another group, and so basically there are 8 computers in the back. Each one is rendering one tile. And there is a master which is broadcasting to each
Yeah.
computer whatever is needed to be run. So it's why you have such a kind of performance. But that's not to be a lot. You have to draw a lot.
I mean, is it sort of just like with the pager on a, Linux screen, and except for here you have a whole computer behind each
Yeah,
thing, but then they're integrated.
And for the neural architecture, it's designed to be very flexible as to what devices you're using to pick up input. So in principle, it doesn't have to be that.
Yeah.
It could be a laser pointer.
Yeah, we're working also on a laser pointer. This one is a little noisy. It's very different where you draw. It can be relatively good, but sometimes.
Yeah.
But to go even farther, I know it doesn't exist here yet, but see these cameras up here? Or other cameras, and neurals, so you see these things here. See, in principle, there's no need to just use something like a stylus as toning machine where you are. So it could be even very, very indirect. So for example, in some of the performance art stuff that I've done, we're looking at using videos to pick up where people are on the floor, right? So that can be converted to an XY and get into the system. And the nice thing about this kind of system is actually quite flexible as to what's giving it.
How you input data.
Yeah. It's extremely powerful.
Great.
Great. Thank you very much.
Very good.
And if you wake up in the middle of the night with an idea, please email me. Now's the time with this very soft iron.
Yeah, very interesting. Actually, nice to see it
Oh, really?
coming to fruition.
Years of, well, a year ago we were talking and saying, well, I remember talking,
Sure.
and I was very happy when Brian said, well, don't really have to have something coded up to have a dissertation, but
Yeah, but now
I'm
you
just
really
delighted.
do.
Yeah. Also, that's why we're videotaping this, because I want to show it to other people.
Yeah.
It's sort of hard to move this thing around. Maybe inspire some students to actually do the real thing. So you should tell Gunnar that you missed
Yeah,
the
well,
show.
he missed the show. Yeah, it's his own damn fault.
It seems
Yeah.
to me things like MATLAB. I mean, for me, the most annoying thing about trying to use it for anything geometrical is exactly this thing of varying parameters.
Yeah.
You do something and you realize, no, this I don't quite want this, and then
And you got to fit in
you
something.
go back
else,
and
yeah.
change, just
Yeah.
it's annoying.
Yeah, no, I mean this obviously
Just to be able to, for instance, even if you type in a function or something like that, which is probably the most efficient way to enter a function usually. But if you want to enter a domain, say, it'd be a nightmare. Unless it's something simple like a rectangle.
And that's the other thing, like even mathematical, are supposed to be a general calculus system. Yes, calculus is calculus on real line. So we can't, I mean, we can write down, I have to go over a wall, but so what, it doesn't know what to do. And oftentimes you just work with the computation, geometric based systems, actually interface thing. Can't do it.
So what's your timetable, Shinwei,
For this thing or for general?
for finishing the whole thing up?
For finishing the thing up, I want to be able to have no more new ideas by the end of June, and spend the summer writing.
Okay, so
doing
then you have to
rewrite.
plan the defense and so on.
In June or in
Well, it can
August?
be August.
Could be late
you know.
summer.
Yeah, I mean, you better find out what the deadlines are, but you know,
Yeah, yeah.
for submitting your thesis.
Yeah.
I think it's really all. I forget. Do you happen to know, Dan, by any chance, what the deadlines might be around there? I mean, my student's fair is
No,
finishing.
I think you have to ask Melissa.
Yeah.
Ask Melissa or something.
Yeah,
But
I'll
the point is,
find
there are
out.
very specific deadlines for when you have to turn in your thesis.
Yes,
You know,
to be
blah,
counted for
blah.
that term.
So what you need
So
to do
maybe-
now, I just realized we better start talking about some of this stuff. In terms of the administration crapola, so because it's interdisciplinary, I don't know quite how this is going to work, but typically, you know, you need a defense committee, which involves somebody from the outside the department. That could be a problem for you. And then a reading committee. So
Yes,
somebody reads
yes, and yes, we have a reading committee on file. I was going to ask you about this because Tim and Mark Quinn here already informed me to be on the reading committee.
Okay, that's
And-
fine. I
and-
mean, all you need is,
yeah,
you know,
I have three. Well, right now it's three intern. Daughter and Lifer is so busy.
well then probably better to, probably better to switch.
Yeah, so I was going to switch.
So are you still living in the area?
Otherwise, a very good friend of mine, she's an expert in working in the
I guess I knew that.
industry in a consulting firm right now, studying organizational behavior. And her background is that she got a PhD in neuroscience.
I wasn't sure. I got some email from him. He just asked me to send something. Gave his home
Psychiatry.
address. So that's what I was wondering.
And she's been working.
Yeah.
I knew her. She,
Yeah.
so I learned a lot basically, and also I met Helga and Nicholas in the summer after I ran Trees on Interaction Media. So
Okay.
and Helga's had a long.
Oh, okay. Well, then that probably
long
that
interest
probably
in,
people probably finished
all sorts of
the
things,
work.
including writing, for example.
Yeah, right.
and rhythm.
Yeah, well,
and
that's
stuff.
one of the things that actually sort of got Shinwei and us together in the sense that we had this same intuition that writing, sort of handwriting, had still something important to tell us about, you know, how people work and think.
San Jose.
Yes, but even mathematics, mathematics. So I started
Yeah.
thinking about writing and mathematics.
Right.
Yeah.
Right. Or I promise that we'll do right. Yeah, I've been writing.
Well, I mean, before I ever got into it.
But I come more from the psychology.
Yeah, no, it's
Yeah.
quite interesting by some of your
Yeah.
comments and
Yeah.
stuff. I could tell. I was trying to figure out what your background
Oh,
was.
well, originally
Yeah.
I was in brain
Yeah.
science,
Yeah.
but I've moved now to sort of the very sort of social part of psychology, and I've been doing work ethnography in organizations. Sort of now I'm going to feel like I'm going to something that I sort of call social ecology now, sort of ecosystems.
So what sort of things? I mean, I'm actually curious what do you mean?
What I mean by that?
Yeah.
Well, to some extent, it's maybe a little bit sort of related to what sort of Latour Bulgar, sort of like the STS crowd has been thinking about, namely seeing sort of like that. For one thing, coming from the brain, I never sort of went cognitive side. So I never thought that the brain was that important. I always thought the brain was just one part connected to the body, and the interaction with the environment had always a lot to do with what the brain actually
Well, of
had.
course they did.
And then I sort of been expanding further
Depends on
out
you
a
getting
bit,
in-
saying it's actually, you know, and as
Sort of
human
naming
we've always been
things.
associated
That's
with it,
people
so we
done
not
that
only getting
forever,
sort of
right?
like
Naming
material
things
clues
in
from
exchange for money. That's okay.
tools
It's-
and other objects, which we do too, and I think that is sort of woefully under regarded, you know. So, and that to some extent the writing, which is the interaction with the man-made symbols that are material by putting them out there, you know, is one important part of that kind of strange interaction. But then also the social interaction, in the sense that we sort of draw on other people as resources to our own
Absolutely.
thinking.
Absolutely.
And so that's the whole thing. And basically, so I was looking, an organization are usually being described either as kind of purely social networks, or they're described as purely sort of formal, you know, it's legal, you know, sort of like things like
Entities, yeah,
systems,
sure.
feedback loops, sort of very much sort of dematerialized, disembodied things. And I was basically
Well, it's somewhere in between, I'd
right,
imagine.
yeah, exactly.
Yeah.
And they're basically both, right?
Yeah.
And sort of how do you sort of put the whole damn thing again together? Basically,
Yeah.
yes, of course, legal structures and power structures do matter, and loops and informational kind of systems do matter, but also, you know, the kind of resources that are material and social
Are
do
very
matter too.
important. I mean, yeah, I just think of sort of how do I carry out my you know, research, and, you know, I mean, it's important to be around other people, but it's important to be around the library and to have, you know, the legal entity of the university to help me do certain things, and,
Exactly.
you know.
So, and it's basically, it's very simple. You know, it's just because we
Yeah.
got stuck in the disciplines in
Yeah.
such different streets, dead-end streets, that the thing that every one of us lives, you know, just hasn't become kind of the starting point or
Yeah, I really think
the focus of research. And that is
higher
good.
education
That's the whole, yeah. So it's a, you know, so that's
Yeah.
unfortunately, and I think that's why we resonated, and I resonate much more with sort of like coming from the collaborative side.
Mhm.
It's like how
Yeah.
does
But how do
the
people work
object-
together? Yeah, right.
exactly,
And how does it help that?
And how does that object exactly make people work together and basically enable them to externalize what
Mm-hmm.
they think, and then have the other person respond to that externalization, and that to me sort of that triangle of that object, you know, and the affordances, you know, sort of
Yeah.
talking sort of Gibson ecological psychology of that object in relationship to the collaborator, the people, where there's both communication
Yeah.
going on, but also interaction
With the object, yeah, no, that's right.
Right, and so that layer.
It has to sort of learn from it in some sense,
Yes.
because, you know, different collaborations are so different, you
Very
know,
much so,
that I think
yeah.
that the object has to
Yeah.
learn how to interact with the people.
Exactly. Actually, that's good,
You know.
because that was one of the things that I was thinking. This is really, it's a huge
Yeah.
task for this thing to become sort of, because of the learning depth, you know, has to be basically infinite, because it has to be able to
Yes.
to
Yeah.
revoke
Yes.
sort of rules established, you know, and
Reset
Yeah.
them, you know, for a
Yeah.
new.
I'm very intensely conscious of this because, I mean, the learning depth here is very deep, but it's deep because of people like François and other part of the team who made it deep. Now, it's impossible for a mathematician to do any of this thing. I mean, the part I
Yeah.
part is just trivial compared to the amount of stuff that's done before. But even then, it's finite, right?
Yes.
Like, you can still
Well,
hit
things
the
are
limits.
ultimately finite, but the
Yeah.
point is, are they deep enough to be useful?
Yeah.
You know.
And I think that's exactly, to some extent, this is like a complex historical snapshot of what mathematics is, you know. And in that sense, I thought it was actually, to seeing that as kind of like in itself, like a state of affairs of mathematics that now becomes the context to the work of specific mathematicians, you know. You can go there and you can draw on surfaces, and you can draw on functions, and you can draw.
Well, that's just it. You know, that's sort of the social background. That's I mean, the word library is a good one because, you know, it is the sort of information that you get from the library or whatnot. You know, and or from, you know, you go down the hall and ask whoever. You know,
Yeah.
you know, hey Rick, how do you do this or that? You know, and if that somehow were, you know,
Right.
stored, you know, and you can just pull that
Right,
up.
right, and that process of basically sort of
Yeah, no. I mean, I would say
embedding
here-
all of these things that you can pull from all sides in your environment into your work,
think
and how
basic-
that
I mean, of
nevertheless
course it
becomes
depends,
of your
it
own
actually
work. I
depends
mean,
on
that's
basic
exactly. I mean, that's at
illustration,
least the
we've had
process
a-
that I see.
basically the-
Well,
That's
very
what
much
the
it's a
authoring-
process that, you know, I think we all feel
Yeah.
happening, you know, when you're doing something.
Yeah.
like
So
this.
this was
Well,
also
that's
the idea
part
of
of
basically
faculty.
knowledge as performance.
Really
that
good.
sort of
Yeah.
made
Well, the
out.
performance is such a loaded word, you know.
I know,
I don't
I know.
like that, you know.
I know.
But
Yeah.
It's hard to find a
Unfortunately,
good
no, there's not a good, you know.
Yeah.
Yeah.
Unfortunately, this is the problem that
Like to change
this
the
is the
meaning.
inflation of good words. You know,
Yeah.
there are all the people that don't want to go really deep. They will still take the word, and then they'll use the word and abuse the word until it's exhausted, and then
Yeah,
everybody
that's the
says
way
it
it
was a
is.
fad. Throw it
Yeah,
away.
yeah,
But yeah,
yeah.
I agree.
Yeah, but this is why I also think of this as a new kind of notational system. So there's this guy Roy Harris who wrote a book about writing, the origins of writing system, and he made this. He's been arguing for a long time that people who study writing shouldn't just think in terms of alphabets, right? Really,
So writing in what context when you say people who
writing
study
as
writing?
like by using let's say, for example, one way to look at it is basically just letters and numbers and alphabets they use to, and in fact, if you think of that as merely a transcription of speech.
Yeah.
Okay, so this is just very limited. I mean, because you can think of writing that's not actually speakable. So, and to the people in this
Right.
field, it seems a very radical idea, but any mathematician
And if you're a
sees
mathematician,
this.
it's the-
I mean, we can speak of it as a verbal gloss, but often we don't actually.
But the point is that writing carries more than just the system of alphabets.
Yeah,
just
it's
like,
not more
you
than
know,
just-
I mean, you know, they're just different things, you know, that happen to have a large intersection.
Right.
Yes, and
Yeah.
it's not just a coding of linear speech,
Yeah.
one-dimensional
No, it
speech
certainly
facts
isn't.
at all. I mean, so going to that area, I could say, look at all this stuff from music notation and from mathematical notation. It's first of all, it's not phonetic and it has a lot of extra structure which is just not unidimensional, blah 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 blah. With deep semantics behind it. The problem, of course, is that not being mathematicians, they cannot understand the notation. So, fine, that's my problem. The other direction is the following: is that, well, okay, like mathematicians according to Royal Harris and many people myself, what's interesting about mathematicians' work over the centuries, and this is found in Helga, is that mathematicians concurrently come up with new ideas and new ways to express them, both. So it's actually demoted usually.
Yeah, no, that's absolutely right. That in some sense, the new notation is part of the whole power of a new idea. You know, I mean, you sort of have a new notation which sort of subsumes a lot of the old notation. It's like, you know, I mean, tensor calculus. I mean, whatever. Something, you know, you look at an old-fashioned book and it's just like, oh my God, how can I ever understand that? And there's a nice, simpler notation nowadays, which is much easier to learn from.
Right, right. And I think this is exactly, and I think in that sense, then the writing becomes much richer in meaning than you basically say.
Well, what that is it's giving it depth. You know, what you're doing is just finding a way to sort of encode much more information in a simpler symbol.
I mean, one
But I think it's also, but that kind of simpler, I think there's a lot behind the simple. You know, because it's like in one sense the fact that, how should I say that? The fact that, for example, you go to a computer and you have to write things in a language where you basically have to say sort of everything
that's very
you
laborious.
operate,
Sure, yeah.
you know,
Very
is kind of
laborious.
takes very or you go there and you actually just pull, or you know, or something like that. So the simple sort of means that there can be an incredible depth behind the simplicity.
See, but that's how the
But we
brain
don't
works,
deal
you know.
exactly, but we don't deal with it anymore.
Well, you don't
In
have to
that sense,
carry
it
it along at
frees-
each step,
exactly,
you know.
right, and it frees sort of a lot of sort of the rest of the energy for other things. So, and that probably wasn't a good example, but it's like, but I just think that's very often that, and I think this is what Trimley means. If you sort of come up with a new notation system or with a new writing system, what you do is also you reorganize what is simple and what's
I fully agree.
laborious.
What's the
and then you sort of
what's just sort of
refocus.
notational
Right.
crapola that you have to, you know,
Right.
on demand be able to come up with, but you don't need to carry it along.
Yeah.
I mean, that's always one of the hardest things pedagogically.
Yeah.
You know, students just sort of saying, look, this looks messy, but there's only half an idea here.
Yeah,
you know?
yeah.
Right.
That
You know,
is-
and it's not very
Right.
hard, but you just got to
Right.
get past the.
Yes,
you know.
exactly. Past the mess.
but it also has real practical consequences. Like, for example, with certain problems in geometry, you can actually attack using differential forms. Okay, going back to Chen and Cartan, and you can get results more brilliant, right? You get amazing results, but it's a very densely coded thing. Or, in fact, I think you can get results you cannot get by going to, work with coordinates and working with.
Well, you get different. I mean,
you get
it's a different
results.
sort of thing. I mean, I think I remember in my own learning process, if you look at a lot of computations you do in geometric analysis, when ultimately you have to solve the PD, you have to get estimates. So Yao's work is a great example of this. That you have all this sort of fancy coordinate-free notation, but ultimately when you got to do estimates, you got to figure out, you got to untangle all this goddamn notation, figure out what you really have to estimate. You have to be able to sort of unwind it all, and that's sort of a hard thing. I remember having a terrible time when I first had to learn how to do that. Because you get very beguiled by this sort of fancy notation. You think, oh, this is all I ever need, And I'd never really adequately learned how to unwind it, and then at some point
you
you
have
do.
to go through the point of unpacking the.
Yeah, that's exactly
That's
right.
interesting. So there is this. There's the opposite to the simple.
Yeah.
You have
Well, no,
something
I mean,
simple
you
and
always
powerful,
have to
and
be
then
able. I mean,
have
this
to
is
be
the
able to
scoping
take
idea
it
that you were
apart.
talking
Yeah.
about. That these things do have depth, and I think that's a hard thing to learn.
Yeah.
I mean, that's part of the learning. It's not just how to manipulate these sort of
Right, it's part of
abstract symbols, but it's how to be able to
It's part
unpack
of the
them.
competence that you also know that there's something behind that you actually can take apart.
Yeah, that's right.
Yeah. Go
Yeah.
to the point, to the level where you need to be.
Have you ever studied notation for dance? I know.
Yes, I know.
That's
For
something I've
some
always
have
wanted to learn something
Yeah.
about. I know nothing
Yeah.
about it, and
They
that must be
they
tremendous.
haven't been as successful as
Not at
musical
all, yeah.
notations. No, there have been different people trying to come up with these things, but somehow
I know
it
Nijinsky
hasn't.
did,
Yeah,
80
Nijinsky
years
did,
ago.
exactly, right. There is Laban, who did another one. I think there was also other dancers that tried to come up with it. It hasn't been really, no unification.
So the point is, it's only survived because of people's memories and now
Yeah.
videotape, and
Yeah.
that's sort of how.
Yeah.
That's fascinating. So really, they've never
Interesting.
gotten.
Yeah.
That's
It is
amazing.
funny.
Pass it down.
It's almost become something like an art object in the sense that the notations itself is something that people play around with. So it's funny. That reminds me because this guy, yeah, exactly.
Maurice
and
Cunningham,
Paul-
yeah.
Did you see
Yeah,
this?
exactly.
Yeah.
And there was this this piece of work that this guy Paul Kaiser did
Yes.
together with Maurice Cunningham. And basically, what he did motion capture. But it was to some extent, and it was an interesting of a ballet dancer, and then he created sort of line drawings that were animated by the motion capture, and with those line drawings, he actually sort of and underlying those was a kind of the dance notation of basically sort of he had almost these things painted on the ground how they were supposed to be doing.
Interesting.
And then it was juxtaposed. It was projected very large behind sort of a kind
Onto
of
a
partial
screen.
screen. And then there were two real ballet dancers, after sort of
And this is very like Twyla Tharp had a thing like this too. What was it? The Catherine wheel.
Oh,
Yeah.
Catherine Wheel,
Yeah.
that's beautiful.
Yes.
Yeah, that
That's
was
really
fabulous.
great.
But you remember these sort of computer-generated
Yeah,
figures
yeah,
that the real
yeah.
dancers were
Yeah.
dancing
Dancing
with.
with.
That was
Yeah.
just a spectacular
Yeah.
idea. Which predated which,
Yeah.
you know? Because that was
Catherine was
This
much
was more
older.
recent.
Catherine
This
was much
I think
older.
that yours is earlier. I think Kaiser
Twyla, I mean,
just
that was like in the
recently.
mid-70s,
That's
it seems
not
to me.
long
Yeah.
time.
No, that was a
This is
spectacular
recent.
But I
thing.
felt that was also, in a way, the juxtaposition was almost like the writing system, which was the dance notation that was
Yes.
embodied in those computer-generated.
Well, no, I mean,
figures.
see, that's ultimately probably what it's going to have to turn out to be. That's how you can store it.
Yeah,
you know?
yeah.
Some sort of writing thing.
And that was sort of a wonderful inspiration on
Yeah,
whoever's
it was
part,
beautiful.
Yeah.
It was very beautiful.
Paul Kaiser. But see, this is it's a middle ground between just taking raw data and like audio. In audio, you can just take sound samples and just get this. And if you see them, they look like a trace, right? Like a sound print. So you can't really read it the way you can read text, or it's not really writing to me, right? But then on the other hand, you have things like MIDI, which is a code, which just tells the machine to turn on at this frequency and so on for so long. And that's in a sense an extreme of writing code. And with dance, the difficulty is that we can just take raw data, videotape, but there's no way to write with it. You can edit it by just
No, I
sampling.
understand, but the
And
point is that we just have to expand what we mean by writing as something
Yeah,
different.
exactly,
This is
exactly.
encoded, you know?
Right, exactly.
I mean, look, they're having the same problem in computer music. You know, they don't know diddly squat of how to,
Yes.
you know, I mean,
For sure.
You know, classical musical notation just doesn't work. You know,
Yeah.
doesn't work.
And it would be interesting to actually understand better why it doesn't work. Because to me, it's like I was thinking also dance notation. There's Alexander. I mean, with I think because it's a capturing there of something that is both.
Well, I think there are many more parameters. Is the point?
Right.
I mean, that's all it is.
And there is a meaning that has to be captured. And I think this is like in the
No, but look with
dance-
music too. I mean, come on, you can you know, you have the symbols, you can play the notes, but
Right.
that the emotional content is something that has to
Right.
come, and that's
But
just
why I
beyond what
think-
you can.
Exactly. That's why I think it's probably in the classical music that one is to some extent more standardized.
By discipline,
in
by
computer,
performance
maybe.
Well,
practice.
it's a social
Yeah.
thing.
It's
Come
a
on,
historical,
this
historical
historical
performance
thing of
practice.
teacher passing on to
Right.
student passing on to.
Right. But maybe I mean, that's why I said I'm not saying I have a solution, but it would be interesting to say why does it work with classical and why does it not work to music? Because that's exactly, then maybe one would understand why dance notations or other kinds of notation, like Alexander's notation for like social interaction, doesn't really work. I mean, it fails, it's all very desirable, but it fails in a critical way. And what that critical dimension is, I think is somewhere in the meaning, whereas in the music, in classical music, it manages to do that.
Well, I think there are 2 points. One is that classical music has fewer parameters than
Yeah, and
either
that's a
dance
good
or
point.
computer
And I
music.
think-
Yeah.
You know, and that's just it. You need
Yeah.
sort of
Sure.
a denser, more
Yes,
complicated
sure.
notation
Yes.
for that. And then I think the computer music community just has not developed sort of the history yet.
Yes.
You know,
and it could be
that
that it is a sense of kind of a
I mean, I don't know if you go back to
segmentation
like
of
Baroque
phrases.
music, for example. I don't know how much you know
Yeah.
about the whole system there, but the point